So Lewis dot structures allow us to use the valence electrons present in a molecule to determine the actual structure of the molecules, what's bonding to what. And in Lewis dot structures, we can have single bonds, double bonds, triple bonds. We never have any quadruple bonds. We also have lone pairs and unpaired electrons. So single bonds represent 2 electrons, double 4, triple 6 electrons. In our last video, we went through some simple ways to draw structures. This is to look for unpaired electrons and then just pair them up. For instance, in H2, here's an unpaired, draw a bond between them. H2S, the hydrogen has one unpaired, the sulfur has two, so I go ahead and draw a bond between the sulfur and the hydrogen and between the sulfur and the other hydrogen. Then when one got to N2, well, the nitrogen, we had to draw a single bond and then a double bond and then a triple bond in order to pair up those unpaired electrons. Now, this works, but not always. So let's go through more complicated Lewis dot structures. And so what we're going to look at is we're going to look at the case of CH2O. CH2O has carbon, 2 hydrogens, and an oxygen. So the first thing we do in Lewis dot structures is to determine the number of valence electrons. If it's a cation, then it loses electrons. If it's an anion, it gains. So for instance, in CH2O, we have 1 carbon, which has 4 valence electrons. We have 2 hydrogens, each has 1 valence electron, and then oxygen has 6. The charge is 0, so it hasn't gained or lost any. So if I add those up, that's 12 electrons. That means that my Lewis dot structure is going to have 12 electrons in it. Next, I draw a structure. What I need to do is I need to figure out what the central atom is. The first thing is, it is never hydrogen. Hydrogen only forms one bond, so it can't be in the center. So, what's in the center? Typically, it's whatever is the least electronegative, except for hydrogen. This means that if fluorine is the most electronegative, it's the one furthest to the left, typically the atom that is closest to the carbon group. If I look at CH2O, carbon and oxygen, carbon is further to the left on the periodic table, so it's going to be the center. I can then draw bonds to the other 3 atoms, to the oxygen, to the hydrogen, and to the other hydrogen. So far, I have 6 electrons here. 2 in this bond, 2 in this bond, and then 2 here. Next, I go ahead and I can place electrons on the outer atoms in order to form octets. I don't do anything to the hydrogen because it already has that duet. So I can go ahead and I can put it on that oxygen. So I have put 6 electrons here. That will give my oxygen an octet. Notice at this point, I've now used 2, 4, 6, 8, 10, 12 electrons. Now, what I do is if I have any extra electrons, I can put those as lone pairs on the central atom. Well, CH2O, remember, has 12 electrons at the beginning. We've used 12, so we don't have any left. So I can't put any lone pairs on that center. Now let's look at our Lewis dot structure. The oxygen's happy. It has an octet. The hydrogens are happy. They have 2 electrons. But the carbon's not. The carbon only has 6 electrons around it. 2, 4, 6. So we have to now go on to step 5. By the way, in step 4, if we draw something and it fulfills an octet for everything, we don't have to move on. But if we don't, we need to move on to step 5. Step 5 is we can move lone pairs to form double and triple bonds. And so if I look at this, if I move one of these lone pairs to here to form a double bond with a carbon, I'm now going to have a carbon with an octet. The oxygen still has an octet. This is my Lewis dot structure. Notice how I have 2, 4, 6, 8, 10, 12 electrons in here because I started off with 12. My carbon has an octet, oxygen has an octet, hydrogens, they only have 2. Finally, step 6, this is where I put any notation. For instance, we already talked about ions. For ions, I would add brackets in charge. Well, CH2O is not an ion, so I don't have to do it. So this is my Lewis dot structure. We'll talk about another instance where you have to put notation next week. So let's look and let's do NCl3. So NCl3, the first thing we do is we determine the number of valence electrons. I do this by looking at the periodic table. Nitrogen has 5. I have 1 nitrogen, so that gives me 5 electrons. My chlorine has 7 valence. I have 3 of those, so that's 21. Adding these up, I have 26 valence electrons to use. Next, I go ahead and I draw a structure. So what's my central atom? Well, nitrogen is furthest to the left, or to put it another way, the least electronegative. Oops, left, not west. So I can go ahead and put nitrogen in the center, and I go ahead and I draw single bonds to all my chlorines. So far I've used 6 electrons. 2, 4, 6. My third step is to place electrons on outer atoms. I want to give those octets. So I have nitrogen, chlorine, chlorine, chlorine. So I can go ahead and I can put 6 around this chlorine to give it an octet, 6 around this chlorine to give it an octet, 6 around this chlorine to give it an octet. Now I've used up 24 electrons. I have 2, 4, 6, 8 around the chlorine on the left-hand side, 8 around the chlorine on top, and 8 around the chlorine on the side. So that's 24 electrons. Step 4. Step 4 is I go ahead and I can put any more electrons as lone pair on central atom. Let's go ahead and do this on another page. So we have NCl3. In step 3, we add this. We started this by saying there are 26 electrons. So far we've used 24 electrons. So I have 2 more. So I can go ahead and put those last 2 on, in this case, nitrogen. So now I can go ahead and I can count how many electrons I have. I have 2 here. So 4, 6. So that's 6 electrons. I have 2 electrons here. 2 here. I have another 6 as lone pairs around that chlorine. I have 6 around this chlorine. I have 2 for this bond. And I have 2 here. So that's 6, 8, 10, 12, 18, 24, 26 electrons. So this is my Lewis dot structure. Notice step 5 would be to make double bonds, but only if needed. Well, I already have a happy nitrogen with an octet, happy chlorines with an octet, so I don't have to make any double bonds. So this is my Lewis dot structure. Step 6 is notation. NCl3, this is not an ion, so I don't have to do that. So here's my final Lewis dot structure. Notice it's slightly different than what I had. I had the chlorine on the top. Either way is fine as long as I have the right single bonds and the lone pairs on the right atoms. Let's go and look at a few exceptions to the octet. We already talked about hydrogen. It only has 2 electrons. Sometimes for beryllium group, that's beryllium on down, we can only have 4 electrons. Boron will have 6. So for instance, BeH2 or BF3, you can notice here the boron only has 6 electrons. We can also have some atoms with more than 8 electrons. These are ones in the 3rd period and below. For instance, sulfur in SF6, it has this arrangement where it has 6 fluorines around it. If I look, this one has 2, 4, 6, 8, 10, 12 electrons around it. It can do this because it's lower in the periodic table. It actually starts to use those d orbitals we talked about. Another instance is IF5. Here, IF5, it has 1, 2, 3, 4, 5 single bonds, so that's 10 electrons and another lone pair. And then finally, we have radicals. Radicals have an odd number of electrons. This nitrogen here, it has 1, 2, 3, 4, 5, 6, 7, so it's not going to have an octet. So that's just one thing to remember in step 4 is sometimes we aren't going to have an octet, but typically the goal is to get an octet. We'll go through a few more examples, look at some very important special types of Lewis dot structures in class next week.